So let's get started. Welcome to our Monday Colloquium series. It's my pleasure to introduce today's Colloquium speaker, Professor Sam Stechmann. Sam is a professor in the Department of Mathematics here at UW, and he arrived here in the fall of 2010. He graduated from the University of St. Thomas. A lot of my kids' friends went there. It's a good place. Up in St. Paul in 2003 with degrees in mathematics, physics, and chemistry. And then he headed to the Courant Institute at NYU, where he earned his PhD under Andy Maida, and constructing mathematical models of tropical convective modes, the MJO, intraseasonal fluctuations and gravity waves, all sorts of things. He graduated there in 2008. And then he went to UCLA on two things, on a NOAA Climate and Global Change postdoc and an NSF Mathematical Sciences postdoc. So Sam's done lots of different things and impressed lots of different people along the way. He's authored nearly 50 refereed articles, 5 book chapters, and given a host of conference talks, invited talks all around the world on a broad array of subjects, including models of the MJO with vertically varying convective adjustment, precipitating quasi-geostrophic equations, and PV inversion with phase changes, moisture transport by baroclinic waves in the PQG dynamical framework that he and Leslie have been working on, stochastic models of El Nino with westerly wind bursts, tropical convection and cloud studies and multi-scale eddy simulations for moist convection, to name, and I mean it, a very few. I'm serious. Take a look at his resume. Sam's modeling approach begins purposefully with minimal complexity, and in order to gain deep foundational insight, and then gradually lacquer on extra complexity. It's a really excellent scientific method. And this discipline, I think, also explains why he's a renowned classroom teacher on campus. He's won several awards for that. And he's won awards for his research work, and I'll mention only the 3 most recent ones. He was an ONR Young Investigator Award winner, a Sloan Research Fellowship winner, and a Vilas Associate winner. So today Sam's going to address the question, can statistical physics provide new perspectives on cloud, climate, and extreme precipitation events? So it's my real pleasure to introduce Sam Stechmann to the rest of you. Take it away, Sam.
Yeah, thanks a lot for having me over here. As motivation, a few of the challenges we're thinking about in terms of clouds and precipitation, a lot of very big ones. Things like uncertainties in climate predictions and how clouds are one of the main uncertainties around. Also in terms of simulation and forecasting, the impact of clouds and their multi-scale variability are some of the most challenging things. And when I make this list, I don't mean that I'm going to solve all these problems by the end of the talk. I'm just saying that these are sort of the broad problems out there among many others in terms of issues related to clouds and Precept. And the challenges arise no matter how you want to look at the problem. If you're thinking about observational data analysis, clouds and precipitation are really hard. Just in terms of questions like, what statistics should I even analyze? There's so many things you could look at in different ways. Modeling and prediction problems, and also just basic theoretical understanding in terms of what are the basic physical concepts you could use to describe clouds and Precept. And so this type of background is what leads us to ask this big picture question. Can statistical physics provide unifying principles for ways to look at observational data analysis, ways to think about modeling and prediction, and ways to think about basic physical concepts for how clouds and precipitation work? So, as the outline, with this main theme in mind of statistical physics and clouds and Precept connections, I'll start off with a background on the observational basis for this connection, and then after that talk about stochastic modeling that helps to solidify this connection a little bit, and a few applications. Okay, and a lot of the observational background comes down to relationships, statistical relationships between water vapor and precipitation. And so just as examples of that, the left here is a map of column water vapor from someday in 2011. And this is, I think, data that comes right from here in this building. And this is just to illustrate basic numbers in case you're not familiar with these. Typical numbers for the amount of column water vapor are things like 60 millimeters if you're in the tropics and decaying as you move away from the tropics. And then at the same time relating that to precipitation. So this is just a map from 2014 to show sort of the distribution of rainfall in the tropics and some of the magnitudes around And to some extent, relationships between these two quantities should maybe come as no surprise. That rain happens when there's a lot of water vapor around. But it really wasn't too long ago that some of the first real clean looks into these relationships came about. And some of the earliest work was by Larissa. And they were not necessarily looking at it with a statistical physics perspective. But then later on, a few others came along and viewed it from the statistical physics perspective. And so one question you could ask is, can we think of precipitation as a phase transition? And I don't mean phase transition in terms of, Clausius-Clapeyron and small-scale phase transition, but literally analyzing satellite data with a footprint of, say, 20 to 50 kilometers, and thinking about a phase transition of cloud systems and things like that. So what this plot shows is column water vapor down here on the x-axis, and mean precipitation is this curve right here. And so this is the basics of this phase transition, that if the column water vapor is below a critical level, the average rainfall is essentially zero. And as soon as you rise up near this critical level, there's a rapid increase in the mean precipitation. And at the same time, that location at that critical value that's also the location of a peak in the precipitation variance. So a lot happens when a system crosses this critical point in terms of rainfall turning on and big increase in the variance.
And Sam, how much
Yeah.
of this curve do people still trust?
Yeah, and that's another tricky thing with a lot of the statistics that I'll show here is, when you're talking about the most extreme points, there's limited data, and there's also the question of how much do you trust this data, since this is the data coming when you are wettest, when there's the most clouds and things like that. I'm not sure that I can speak for a broad audience, but there have been a lot of questions raised in terms of how much of this is truthful. So like in this particular paper, these are actually details I wasn't going to plan on going into, but I'll mention them in this context, that I'm not going to talk about these details, because to me, I guess what's most interesting is that there's a rapid increase and a peak in the variance. And those features I don't think anyone's going to argue too much with. There are other details with the statistical physics perspective that Peters and Nealon looked into, and these include things like power laws in a variety of things, like that. This curve right here is a power law, and it's questionable whether this is really there or not, depending on how you look at the data. I'm trying to think where other power laws. There may be a power law also extending here, and I guess this inset is showing the power law in the mean precept. So I'm actually not going to talk about too many of those details, because even without those details, there's a lot of interesting questions in terms of just the broad picture that's here. Yeah.
And just to be clear, when you're talking about the preset mean and variance, you have some sort of footprint that you're looking at called water vapor, and you're looking at the mean of that footprint compared to the variation of the subgrids, of the sub
No.
footprint scale.
No.
Oh.
Yeah, a simple way I could explain it, which isn't precisely how it's done, but would be, say, pick a XY grid point, identify the column water vapor, find which bin that column water vapor is in. I then have an ensemble of precip rates, and then I'm plotting the mean and the variance of all those. It's a little trickier than that because when they originally did this analysis, the precip and water vapor data had different resolutions and things like that, but that's more or less what it
Is this ocean only?
is. In this study, I think it was.
It is, yeah.
Yeah. And so what this looks like, if you're unfamiliar with these types of things, would be stuff like classic models like the Ising model. These models go back a long time. So the Ising model would be characterized by a PDF of spin state sigma. So down here would be a couple of illustrations of sigma. It's a discrete variable, either a 0, 1, or a plus or minus 1 type of variable. It lives at each one of these XY grid points. And this PDF describes the likelihood of any particular one of these configurations. And what you find is that as you vary, say, the temperature, which is this parameter right here, you will go from a state that has all the spins aligned, so that the mean magnetization of the system is roughly 1, and it'll decrease down towards 0, as you can see from these illustrative figures here. And very interesting things happen around the critical temperature, which here is about 2.3 or so. You can see there's a peak in the Chi means susceptibility, but you can also think about it as variance. The two things are closely related. Yeah, so it's what we saw on that previous slide. It looks like it fits this type of picture pretty well from a crude perspective. One difference I want to point out is that these types of models often, but not always, are developed in terms of discrete variables. So it's not necessarily immediately obvious how to connect these types of classic models with what is being seen in the atmosphere. Another aspect of this is not just phase transitions, but criticality and self-organized criticality. So what this plot shows is the same mean precip along with the PDF of the water vapor values. And what you see in this plot is that the system loves to hang out near that critical point, just below it actually. And so one way to crudely characterize this is that the system self-organizes itself to be near the critical point. People introduce this extra word, self-organized, because, for instance, the Ising model we just looked at, that temperature is a tuning parameter that you would adjust in a lab. Whereas here, this is the climate system, and it just decided on its own that it wants to hang out near the critical point more than anywhere else. So that's the basics of the observational background. And I guess one question that this begs is, what would be a modeling framework that could help explain what happens in the atmosphere? So in other words, can we think of cloudy and clear skies as being kind of like spin up and spin down phases in some way or another? And are there simple mechanisms for how this might work? Something analogous to how the Ising model works for ferromagnetism, but something that would explain cloud regimes. And I partly say this to indicate how simple I'm thinking about. Thinking about a quite simple model here, with a few parameters, even though you could think of something more complex if you wanted to. And the hypothesis we came to, and that we'll talk about now, is maybe turbulent advection diffusion of water can reproduce the statistical properties that we were looking at. So as a simple model of turbulent advection diffusion of water, atmospheric water, water vapor, we're going to write down a stochastic PDE that takes this form. So we have only one variable here, just the column integrated water. And at first glance, you might look at this and think, how would this be related to actual atmospheric dynamics? But if you think about it a little more, it's actually somewhat reasonable. So if you took the actual equation that would be satisfied by column integrated water and broke it up into resolved and subgrid scale components, Q bar and Q prime, the resolved component would evolve according to these terms on the right. The primed terms could be represented as an eddy diffusion, certainly a crude way to represent it, but not crazy. And the other terms would be the advection by the resolved velocities. And for this model, we're not going to try to model those. You could try to model those using fluid dynamics, but we're going to try to come up with some statistical form for them. So one simple way to represent this turbulence stochastically is to introduce random forcing. W dot is space-time white noise, and capital D is the magnitude of that noise. And then in addition to that, it's useful and needed sometimes to have an additional damping term involved too. And so that leads to this equation here, which is more or less the stochastic heat equation. There's heat or diffusion right here for the spatial interactions, the stochastic forcing term, some relaxation, and F is just a constant that we'll use here. And I present this here and I state this hypothesis as if like this is how we set out to go about this, but this is absolutely not the way things actually work. We never would have expected this model, a linear model, to do anything all that interesting at all. And I'm sure maybe you wouldn't have either. I mean, if we're talking about clouds and precipitation, the first thing you usually think about are nonlinearities and complicated things like that. So we set out to look at this as a warm-up, just to get some codes written and things like that. But I'll show you some indications for why this actually is a pretty good model. Yeah.
So the random forcing in here is like a Gaussian type
Yeah, Gaussian, in fact, independent spatially and independent in time. We'll be solving this on a lattice all the time too, because this equation actually doesn't even make sense from a math point of view. It would have an infinite variance for some technical reasons, but it makes sense perfectly fine if you used a spatial correlation to your noise or if you have a lattice. And then you have to talk to you about that if you want later.
Well, so the advection in a short time scale can be pretty nonlinear, but it seems to be a diffusion in a longer time scale, and more like, which is like a relaxation. So maybe sort of for longish time scales, however how long that is,
Right.
then it would be somewhat diffusive. Is that
Perhaps, yeah. That seems reasonable to me too. And I guess the other thing to keep in mind is this is perhaps not a great model if you really want to follow around the individual details of how the water vapor is evolving. But it maybe is a good model for the statistics of how water vapor and clouds are behaving.
Is the forcing the combination of the W dot term and the S term?
The S term for me is just going to be a constant. Just there to help set the, when we get to defining clouds, just sort of sets the level of where the clouds are. One indication why this might have something to do with statistical physics is that, so if you take the continuum version of this and go to a lattice, so now instead of x and y, we have lattice locations ij. You can write down the PDF for those Q values, the stationary PDF, and just from a crude association, it actually has roughly the same form as the PDF of the Ising model. So the temperature of the Ising model is similar to the magnitude of the stochastic forcing, d, or d squared. The spatial interaction term of the Ising model is like the diffusion coefficient, the eddy diffusion coefficient. And the external magnetic field H is a lot like that external forcing term F, along with some other terms that pop up too in this equation. But this is sort of helpful in terms of if we want to know about how the stochastic heat equation might behave, then we have some intuition based on how the Ising model parameters dictate the behavior of the Ising model too. And it also suggests that maybe this analogy would suggest that there's similar model behavior to some extent. Although still in the back of my mind I'm thinking this is a linear model, how can anything really interesting come out of it? So to model clouds, we're going to use a cloud indicator, and it's just an a posteriori thing, just for data analysis. So we say there's no cloud if the water is below a saturation level, Q star. And there is a cloud present if water is above a saturation level, Q star. So sigma, the cloud indicator, is just the heavy side acting on Q minus Q star. So if this is a snapshot of Q of X and Y, where red is lots of water, then this would tell you where that water is above a certain threshold. So there's a blob of clouds here, another one down here, and so on. And just to emphasize this, this quantity sigma, it's slaved to the Q dynamics. It has no feedback, so there's no nonlinearity in the underlying dynamics. Although interestingly, we can look at the statistics of sigma, and it's a nonlinear quantity itself. But still, you have to keep wondering, and didn't really think going in that this would give anything realistic, but we'll see here in a few slides now. So as evidence for how well this works, we're going to look at comparisons versus some of the observed statistics, and from sort of three-ish different perspectives. One is the phase transition perspective. Another one is cloud cluster size statistics, which may or may not be related to this, depending on how you look at it. And then a third part of this is spectral power, which I would not normally associate with either one of those. And I just want to emphasize that we're looking at a wide array of different types of statistics with a model that has 3 to 4-ish parameters. So it's not like we're just tuning parameters and then getting statistics. We're looking at a much wider array than the parameters we have available to us. So the first piece of this is the phase transition. This was a plot we saw earlier, and the model also has this type of behavior. The critical point is, I think, about 63 or 67, somewhere in that range for the model on the right, and the PDF of the water vapor is tucked up right near the critical point. And I should say this is work with a former postdoc, Scott Hudeby. And again, like we were saying earlier, I'm not going to talk about power laws or any other behaviors here. It's more just some of the cruder, coarser aspects of this. Yeah.
Can you remind me, the blue and the green on the left are?
Oh, I guess I didn't distinguish those before. So the green is the PDF of all water vapor points, and then the blue is, if you only look at the points that are precipitating, this is the PDF of the water.
And then on the right-hand side, this is just the...
Analogous to the green, yeah. And other details that I'm not going to talk about here are these PDFs have exponential tails to them, which are really neat. This model on the right does not have those. Although other models we've looked at, if you introduce other nonlinearities, they can pick up those tails too. And the next piece of this is the very, go ahead, yeah.
One more question.
Yeah.
If you introduce, if the noise is state dependent, that also introduces those interesting fails?
We did not need state-dependent noise to get it, although I could imagine that would also influence it too. Yeah.
So in the model, what was the precept?
Oh, sorry.
You talked about the cloud.
Sorry. Yeah. That's going to come up in a couple of slides from now, and I'll show the precise formula. But you're not going to be surprised by it. Right?
Oh, okay.
Yeah. Yeah. Thanks. And the variance, also, it has a peak roughly near the critical point in the model. And if you're thinking, what's going on with these error bars and why are they so gigantic? It's because we thought we should analyze the data pretending like we have the same size of a data set available as they did in the observational data. Although for some other statistics I'll show later, we have teeny tiny error bars because we wanted to make sure we were truly seeing what we were seeing. And another neat aspect of the variance is scaling properties. So if you look at the variance after averaging over different sized blocks, maybe if we skip down to the bottom here, trivial scaling would be that if you had independent variables, random variables at each box, and you did this averaging, then there should be a power of 2, an L squared scaling in the variance that you compute. A non-trivial scaling would be L to some other power that's not 2. In the observational data, like they were seeing here, you'll see there's actually many variance curves plotted on top of each other. That's from doing this type of calculation on different scales. And they all collapse on each other if you scale by L to the 0.42. In our model, if we get different, depending on which L we pick, we get different variance plots, and they all collapse onto each other if we scale by L to the 0.6. So not horribly far off for something this simple. Oh, and I guess I should say, why are we looking at this? This is sometimes suggested as evidence of criticality, that there's non-trivial scaling, spatial scaling going on. Okay, now the definition of precept. So this is one plot I like to show just because it's sort of the basic features going on here. On the left is that snapshot from trim data, and on the right this is a snapshot of rainfall from the model. And our definition of precept that we used here has 2 parts to it. The first part should look somewhat familiar. It's just proportional to how much water is above saturation times a Heaviside function. We add on an extra component to it that's just a constant times the Heaviside function for other reasons. It doesn't really matter which, for like making a plot like this, it doesn't really matter all that much. And in some of the earlier plots, we've made them with a variety of turn this one on and this one off, and they all, if you're just thinking about the crude picture, they all do the same thing. Yeah.
How do you set the relaxation time scale?
Oh yeah, that parameter would be set coming up here in a slide or two. Yeah, I'm trying to think if I should say any of those other ones now. Yeah, how do we pick these parameters? Q star we set based on the the average column water vapor we would want. Q star and F together. They actually are more or less the same parameter. Those are just two additive constants. So those two were set just based on average column water vapor to some extent. And D star comes from, that sets the overall variance. So the variance of the column water vapor will tell you D star. B and tau are related to spatial correlations and temporal correlations, and I'll show that in a couple slides. Yeah, so just from this type of picture, it looks like the sizes of these clusters are somewhat comparable to the eye. And to look in more detail, on the left, this is the distribution of cluster sizes. So you would look at one of those snapshots and make a bin of like cloud area. So grab a cluster, find what area it covers, and count it in one of these bins. And in observations, people find that this distribution, the number of clusters with a certain area, follows a power law distribution. Several different exponents have been seen depending on how people have looked at the data. So here they're seeing 1.66 to 1.87. When we look at this in the model, we see something around 1.73, which is in the same realm. Yeah, so there are lots of little tiny clusters, not so many large ones, and this is a really interesting quantity because it really spans many orders of magnitude from like individual smallest cluster you could imagine, getting close to the planetary scale even, in terms of like cloud length, or maybe not planetary quite, but synoptic or a little bigger.
Are these clusters precipitating clusters or total cloud?
Either one would give the exact same
Oh, okay.
statistic here. I'm trying to think. I guess another quantity you could look at though to distinguish would be the, I'm trying to think about what it gets called. I can't remember the name that people have used, but if you also say integrate the precipitation over the cluster area, so something like rather than just integrating the area element, integrate precipitation at one point times and then integrate that over the area. So it gives sort of an magnitude of precipitation built into that too. And I think people have seen power laws in that quantity. And the last piece of this is the power spectrum. So this is you can just think of it as the variance of the Fourier coefficient of water vapor in terms of spatial wave number k and temporal frequency omega. And I show this as if this is the actual power spectrum on the left, but it's not. This is the actual power spectrum after sort of averaging it and smoothing it. And from one perspective, you could say, you know, you're kind of hiding and lying here, but on the other hand, you would say the model doesn't have all of the things that are present in nature, like equatorial waves and things like that, which would shape the real power spectrum in different ways. So to some extent, this is a good comparison because it's perhaps the power spectrum that nature would have if the Earth weren't rotating at all and had no dispersive waves. And so from that point of view, there's a reasonable match between the two. They both indicate space-time red noise in the sense that the largest power is at lowest or reddest frequencies in both space and time. And this is where the choice of those two parameters, B and tau, can come in. So those can be chosen. They determine the fall off of power with frequency. That's what tau would do, and the fall off with power with wave number indicated by B. So looking back at these different pieces here, suggests that maybe statistical physics can provide a unified viewpoint. We've seen observational data analyzed from this viewpoint. To some extent, it gives a theoretical basis, a way of thinking about clouds and rainfall with statistical physics concepts and stochastic models. And I should point out one of the goals in designing these models was to get something somewhat process-oriented. I'm not sure you would necessarily think of this as process-oriented when you think of the words process-oriented, but perhaps more so than using a discrete model like the Ising model or a cellular automaton model. At least here, when we use water vapor and its dynamics, we can sort of try to relate the different terms in the equation to what would actually be in the water vapor equation. Yeah.
So in thinking about your mathematical analogy for an abrupt fall off in total cloud liquid water in a column versus the model, that model was, as I understand it, was for a low temperature magnetic situation, and it's regulated by KT. Is there one that's closer to water, such as just the distribution, Maxwell-Boltzmann distribution? Can't you use like the upper 10% will evaporate or the lower 10% will condense? Is that possible to use that Gaussian distribution as a more direct
As a foundation for the phase transition
relationship
behavior?
to, yeah, the column, water
Yeah.
column?
Yeah, if you want to think about any one of these individual aspects, like if you want to think about this particular increase in mean precipitation, you could use an even simpler model than what I've showed you here. If you want to get all of these things together under one umbrella, then it might take something more complex like this, and that's where our goal was. Yeah, so for instance, like Larissa and others had a paper of their own where they looked at the idea of just random water variable and the threshold is one way to summarize it. And to some extent, you could argue that those are the ingredients that you would need to be able to think about this type of an increase. If you have something about randomness of water vapor and applying a threshold. Those
And we
two
got the
things.
variance too.
Yeah. So if you just want to care about that particular aspect, then yes.
Are all those mean precip events simply unusually warm column amounts?
A neutrally
Warm column, because of the,
Um,
saturate, if it's colder.
I don't think it has to say anything about neutrality.
No?
Yeah.
So the threshold in this case is Q star.
Yes. Yeah.
And so your heaviside function is just if you're above, if Q is greater than Q star, then
Yep.
call it, and then that gives your range.
Right. Yep.
Can you elaborate on F? Is that just
In what we just saw here, I guess you maybe I'm trying to think if you even need F then. Maybe you don't even need F. I guess F sets the mean column water vapor value still. So maybe those are, if you really want to connect with the underlying physical situation, those are maybe distinct parameters. One of them sets the mean column water vapor. One of them sets your choice of the threshold for clouds and rain.
Sure, always, I mean, F is a positive number. So you're
Yes.
always adding water over.
If you subtract off the mean, you could subtract off a quantity related to F, and then have a system where F is not part of the dynamics at all. And if you're worried about this, how it's weird, if you're thinking you're adding water in with F, how are you taking it out?
Yeah.
You can also think of F as just setting the mean. So if I look at the quantity Q minus, I think just Q minus F, that may, there must be some scaling parameter.
Q's for
Yeah, something like that. You could take F out of the system effectively. Because I know what you mean. Yeah, that does seem a little funny like that. But there is also always this damping term, that the term the tau, that's pulling you back even though you keep adding it in. So that would maybe be the counteracting term, the tau term.
It requires, I think that requires Q star be not equal to, okay, I see where you're getting, never mind, yeah, I see where you're getting.
Yeah, and maybe the third prong of how you might look at these types of problems in terms of does this really provide a unified viewpoint would be prediction or modeling, and could this be used for convective and cloud parameterizations? And I'm not sure if anyone has literally taken these ideas and built them into a cloud parameterization, but there are some convective parameterizations out there that are using stochastic processes and things like that, and to some extent are relying on similar ideas. To some extent. Although I feel like that would be really interesting to try to build these ideas into a convective parameterization. And I guess the next question would be some applications to all this, since a lot of what we talked about so far was just assessing this connection and seeing to what extent is it true. So next up will be two applications. First, extreme precipitation events. And these are, I'll start off with some observed statistics, and these are really cool statistics. So if you look at the PDF of event sizes, so look at how much rain falls in an event and make a histogram of all those events. So down here we have various event sizes that you could look at, and we'll measure event size in millimeter and ask how many occur for each event size. Not too surprisingly, there are a lot of small events and not so many large events. What's kind of interesting though is they all have more or less the same shape, and these are from locations all over the globe, including even NSA, I think, is up in Alaska. I mean, these are from everywhere. There's tropical sites, Darwin and Nauru, Point Reyes on the west coast, southern Great Plains. I can't remember if it's Oklahoma or Kansas, one of those two. So these are all over the place, and they have the same form. And I guess the other interesting feature is that this would suggest that extreme events should occur somewhat frequently, since this is a pretty slow decay relative to other types of decay, say exponential or something like that. And it also hints at universality to some extent, in the sense that these all have roughly the same shape of their PDFs across diverse climates. So maybe there are some universal features to precip events, at least statistically. And perhaps then also some fundamental mechanisms that are underlying this stuff. So this is slightly different than the previous curve in the sense that they rescale the event size so that they could get even better collapse here.
So what about the slope?
In terms
It's
of,
ultimately got to be physics in origin.
right?
And yet, it seems like all the equations are sort of wired to give you a power law. What determines the slope of what you've done so far here?
I'm actually going to use a different model to get at this statistic, because for this we actually found that we need nonlinearity in order to get at this. But yeah, we'll also get an analytical slope out of it too for the exponent there. So one analogy with statistical physics here, what would be a rainfall event in a statistical physics model? One thing would be from the sand pile model, the self-organized criticality. The way the sand pile works is you have a pile of sand, discrete little sand particles, and there are what are known as avalanche or toppling events, where you drop a new particle of sand, it hits the top. There are various rules for how the sand should topple down until we decide we should stop. And so you can take the duration of an avalanche as a measure of its size, and this statistic also has roughly a power law decay. So this would be one analogy from current statistical physics models that are out there. But again, these are discrete models, cellular automaton models, and so another question would be, how can you model atmospheric processes like water vapor and its dynamics to get at these types of ideas? So this is one version of our model. This is work with David Nealon, and I'm showing the later, simpler version. We had a more complex version from before, and again, it's the same thing every time. You can do a more complex model, and it'll be able to get more interesting looking statistics and more interesting behavior. If you do a simpler model, you might not get as many statistics, but you can understand it better. So I'm going to show you the one that you can understand in just a couple of slides here in this talk. So this is dynamics of water with a threshold for beginning and ending a rain event. So we have a stochastic differential equation for Q, although it's a really simple one. It's just, say, a constant moistening rate and a random noise term. And at this time, we would be moistening while we are not precipitating. So we'll say sigma equals 0 right now. And this will keep happening until we hit a threshold, a critical value. And after we hit that, we come down and we start raining. So now we have a rain rate R, and we're losing water vapor, along with a different random forcing term. And we keep following those dynamics until we hit a different threshold, Q NP, Q not precipitating. And then just keep repeating over and over and over again. So the dynamics would be something like this. Column water vapor, we're moistening gradually, we hit this threshold, and now we lose water and we rain until we hit the lower threshold. And start over, repeat. And there's no spatial variability right now in this. This is just one location, and so you could imagine that any spatial interactions are lumped into this random forcing term.
And there's no dynamics either.
There is dynamics, I guess. There's time variability, time evolution.
There's no vertical motions or
No,
anything.
oh, right, yeah, no
Yeah, that's
vertical
what-
motion at all in this model.
Okay.
Yeah,
Just piling up water vapor until a catastrophe.
right, yeah. And this model has a theoretical event size PDF that looks like a power law with an exponential tail on it. And this comes from first passage time theory. It's a problem you can work out analytically to get this formula for the distribution. This exponent here is 3/2 in this model. And what we latched onto here is in fact not the interestingness of the power law, but in fact the interestingness of this transition to an exponential drop-off. Because really there's this cutoff where you start the exponential drop-off at a large event cutoff, SL, and that cutoff, it protects us, it protects humans and everybody from the largest extreme events. Like if this kept going as a power law, then these would be even more likely to occur. And so later, we analyzed similar statistics in global climate models, and I say we, but really this is David Nealon leading this study, and find that in climate models, the Precept data conforms to the first passage time theory as well. More so in certain regions than in others, but nonetheless, it still more or less follows this type of setup. And more interestingly, if we look at global warming and see how these statistics change, so now there's 2 curves for every location, and they are broken up into, I didn't write down the years, but there's a historical part of the run and a future part of the run with global warming scenario. And what you find is the biggest change is down at the largest events. So what more or less happens is that cutoff scale gets shifted to even larger values. Otherwise, the rain events are more or less unaffected in terms of their statistics. So when this thing shifts, this is now exposing us to unprecedented extreme events. And in the paper, we show some more details of this, like the ratio of the probabilities. And I guess even from these plots, you can notice that there are unprecedented events that now happen under global warming. Yeah, and I guess one neat thing of this picture here is a lot of times when you think about global warming and impacts on statistics, you think about Gaussian variables and how do they change? Do you get a bigger variance? Does the mean shift and things like that? This is a type of a variable precipitation event size that's a positive quantity. Maybe a fundamental distribution for that would be something like this. And now this theory indicates how it would change under global warming through a shift in this cutoff.
Do you have a physical interpretation? Or is there a physical interpretation in this paper? Or
Yeah, so I guess one thing I didn't put down here is the form of this cutoff. It involves the parameters of the model, which are mean rain rate and the variance, the magnitude of the stochastic forcing. And so the hypothesis would be that there is more variability in the globally warming world, and that is causing a shift in the cutoff here. And I guess I should have written that formula.
so that's the stochastic term is
Yes,
more
that's right.
variable. Okay.
Yeah.
Jim and I were just asking this under that question as you were answering it. Can you repeat?
Yeah, sure. Larissa was wondering, do we have an explanation for what's going on and how this works? And that's exactly right. I mean, and this is part of what we hope you can get by not thinking about not discrete automata, discrete models and cellular automata models, but thinking about tying this to the dynamics of a variable that's literally in your model, even though it's not the same dynamics exactly. But this cutoff SL, I'm sorry I didn't write it down, but it's related to, there's only 4 parameters here in this model. It's related to things like the rain rate and the strength of the variability. And so the hypothesis would be that in a globally warmed world, there is more variability around, so this would be a larger value, and that would then shift your cutoff to the right.
And R is constant.
And R is a constant. That was one application, and I wanted to talk a little bit about a new application, clouds and climate uncertainty. And before I get into it, I should mention that these were great in the sense that there's observational statistics to compare with and everything fits nicely together from both sides. This is one where I'm pushing forward a little bit on the modeling side because things looked intriguing, but we have not started the observational side of things yet. And I'm hoping to talk with Tristan LeCoulier some more, or maybe with someone new, to try to figure out how to put that together. So as some of the motivation, in terms of clouds and climate uncertainty, this is one example paper, or one example title, indicating that boundary layer clouds are at the heart of the uncertainty seen in climate models. And so now we're talking not about deep clouds and extreme rain events, but about stratocumulus clouds, clouds that are down near the boundary layer, and although they cover huge areas over the oceans and sometimes over land too. And so our question here is, can we maybe use stochastic models and statistical physics to understand clouds and climate uncertainty? And so some basic thinking here would be maybe different cloud regimes correspond to different phases. Maybe open and closed cells of stratocumulus correspond to things like spin up and spin down in a statistical model. And so to try to pursue this connection, one thing we've looked at a little bit is stochastic models and planning things to maybe look into it from observational data, although nothing there to show at the moment. So just to look into this with the models, so the target would be that in observations there are different cloud regimes or cloud phases maybe. There's closed cells, open cells, pockets of open cells, which kind of look like critical clusters from Ising Model and things like that to some extent. And then maybe shallow cumulus is little tiny clouds with not much large-scale behavior. And if we take the stochastic model, the same one we were talking about earlier, and just vary some of these parameters, now treating the water as boundary layer water only, then we can also get those different regimes to some extent. There's a very cloudy regime, which we could call closed cells, a less cloudy regime, which we could call open, and partway in between the two is an interesting regime where it's a mixture with large-scale correlations, which maybe corresponds to pockets of open cells.
Yeah, I'm sorry, and what parameter did you say you were varying to make that happen?
Yes, I'll show that right here.
Okay.
It's, so two of the main ones would be F and D. F meaning here the average amount of water source being added into the domain in some sense, and D meaning the strength of the turbulence in the domain. Although for us these are, you probably think of those quantities as being interactive and everything, although for us those are things we tune at the moment in this model. And so closed cells in this model would correspond to, I guess I should say, F is not just sources of moisture, it's the net sources. There could also be losses. In this model there's not much interactive physics, so it's all just net quantities. So Precept would count against F. And so closed cells are this point with a higher F. Open cells would be this lower point. Pockets of open cells reside in between near a roughly zero net water loss and gain. And then shallow cumulus would correspond to a more variable, more turbulent state off to the right. And just to indicate how sharp this transition is, this is the exact same data but just plotted in 3D. So this is a really rapid change in going, a small change in F leads to a huge change in the mean cloud area fraction here, sigma. Yeah?
What's the difference between open cells on the left and shallow Q?
Yeah, so in this model, it's hard to distinguish them, and that's partly because we don't really have cells in this model. In a different version of the model I'm trying to work on, we've included some other aspects of clouds that might include cellular structure, in which case there would be a more identifiable difference between the two. At the moment, it's based on the strength of the variability or the turbulence. And so the hypothesis would be that there's a more turbulent boundary layer in some measure for shallow cumulus compared to open cells, which have a larger scale to their spatial variations as a hypothesis. And the nice thing about the simple model, it's missing all these interesting things, but at the same time, what's nice about it is you can write down exact formulas for this quantity. So this is not something we had to find with lots of numerical simulations. This is just a formula. And we can likewise look at climate sensitivity by taking the derivative of the cloud fraction and ask, how does cloud fraction change if, say, the forcing or the net water changes? And this really highlights that small change in F leads to a huge change in the cloud area fraction. There's a giant spike in this climate sensitivity quantity at this location where the phase changes a lot. And so this hints at, maybe this is why shallow clouds create so much uncertainty in our predictions. Maybe they are very sensitive to changes in net moisture gain and loss in terms of their cloud area fractions. And this is all at the level of hypothesis. We don't have any firm connection necessarily with observational data at the moment, but it sounds intriguing to me at least. And so to summarize, the big picture question we were looking at here is, can statistical physics provide new perspectives on clouds, climate, and extreme precipitation events? And I showed some new stochastic models that simultaneously embody the statistical physics ideas, but at the same time can be linked to atmospheric processes, or at least more so than if you had a discrete type of a cellular automaton model. And perhaps this could lead to a unified perspective of observational data analysis. What should we look at? Theoretical concepts, and maybe even how to design convective parameterizations and things like that. And a couple of applications, extreme precipitation events, which has been worked out in more detail from different avenues, and clouds and climate uncertainty, which I find intriguing, but is still very much a work in progress. Thanks a lot for your attention. Yeah.
So, following up with the discussion of what that F is, I don't think it's defines the mean state. And it looks like most of your analysis is tied to over-ocean observation.
Yeah.
I think that's best considered as the latent heat flux from the ocean. And you said that both your shift in S sub R or whatever,
Yeah.
showed the climate sensitive. That was a function of both F and the variance.
Right.
It seems to me like your final one was showing that this hypersensitivity was a function of F. To me, the link to the climate is that you're warm in the ocean, you're changing the latent heat flux, and that variation of F is probably the most critical. That you should think of it as this force system.
Right, exactly, and that's one thing that we're working on right now. We're trying to write up some results where we take this last model, or even a column version of this, and we use, nothing's interactive here, and that's what makes it a little hard to connect with actual physical processes. And so we put in interactive radiation, and we put in an interactive surface flux and things like that, and we still see a lot of the same behavior here in terms of the phase transition, and that's exactly what we're trying to get at too, because you would like to think of, say, either your sea surface temperature or meridional heat loss into the mid-latitudes, for instance, if we're thinking about tropical data, as your tuning parameter here, and let everything else be more interactive. Yeah, so those are things we'd like to get at more. Although for the moment, there's a lot of things lumped together into it.
I don't think you said very much about assumptions about duration. Were a lot of these statistics for rain systems that all had the same time scale of duration? Or were the durations a function of length scale, or what was happening here?
In the observational data or the model data?
Yes.
In the model data, in the Precept event model, there was no spatial variability, so it's all just one spatial location and looking at time series. And that was partly because that's how the observational data was also analyzed. It was arm sites with time series of Precept data. Yeah.
Because some of the climate data for extremes in the world on many durations
Right.
Sort of looks like a power law.
Uh-huh.
Is that consistent with what your approach is now?
Power law with respect to
Duration.
Duration. Yeah, so these types of observational statistics, if you look at duration instead of event size, you also see very similar type of behavior. You also see the same type of behavior for dry spell duration. So if you look at how long you have to wait between the rainfall events. And maybe along these lines, I'm going to mention one other interesting thing that we found. So we were looking at temporal autocorrelations of the Precept data. The precipitation time series, the autocorrelation rapidly falls off. But then there's a really long power law decay that goes into days. And so, when you first look at that, you think that has to be the signature of extreme rainfall events that are long lasting. And when we went into it and analyzed it more, what we discovered is that it's not at all. It's actually the correlation between two spiky rainfall events that had many days of a dry spell in between them. And so in a different version of this model, we took a different limit where rainfall events are literally just spikes. You get a spike of rainfall, and then you wait a long time until another one. And you can see this type of behavior also. Yes, there's a whole slew of different ways of looking at this in terms of durations of the rain event, the dry spells, and things like that. Yeah, John.
It's Monday, so I get to ask a naive question that may have little or nothing to do with your talk, which was excellent. In a warmer climate, is precipitation efficiency reduced or increased? Because isn't there microphysics lurking behind the curtain here? That I know it's not included in what you have now, but at some point, when you keep digging down the way you do, you get to more complexity. Isn't the microphysics going to be a big issue here?
You would think so. I'm not sure if I've seen. I maybe have not seen everything that's out there, but I'm not sure if I've seen precipitation efficiency analyzed under global warming. People definitely look at like intensity and frequency and things like that, but I'm not sure I've seen efficiency. That'd be an interesting thing to look into. Do you know? Or
The basis of the iris.
oh, is it really?
Yeah, that box is interesting. People have looked. I don't know what the most recent analysis of that is, but I mean, it is something a lot of people.
Okay,
I'm not sure that there's a clear answer on.
that's my crude understanding too. I'm not sure that I've heard a clear answer on that. Yeah. Yeah. Interesting. Yeah.
I think the cloud and climate sensitivity analysis, it's been the same thing that said Brad in terms of that the mean, the mean evaporation rate. It's really a mean accumulation in the layer. So if you have some sort of, if you're in the trade wind regime where you're ejecting moisture, there's a evaporation, the net evaporation occurring, and maybe a net effect of transport as well. But whatever the case, there are a number of climate diagnostics that could be looked at to identify what is F in the stratocumulus region, and what is F over in the western subtropics, whereas
Right.
you don't see this sort of.
Right. Yeah.
I think
Yeah.
there's a lot of there's some really interesting diagnostics.
Yeah, I'd be interested in hearing what you think. We started to look into that a little bit with Tristan, and we haven't found anything amazingly conclusive. And it's partly because there's so many things lumped together
Yeah.
into that F, interactive and not. But yeah, other ideas would be great to hear. Yeah,
And this is just a slight criticism.
yeah,
I think you're searching for open cells in your model. I don't think, with just a 2D model, I don't think you can get open cells. You have, they're formed by updrafts and downdrafts.
right. Yeah, yeah. I'm
So
trying
I think
to.
you're kind of stretching the.
Oh, yeah.
Open cells.
Yeah. Maybe there should be in quotation marks.
Yeah.
Certainly in this version of the model, there's nothing cellular.
Right.
In other versions where we've added some other nonlinear processes into it, we're hoping that perhaps you could see some cellular types of structures. In the end, for the question of climate and clouds and climate uncertainty, it's unclear if you're just thinking about these crude statistics how much the cellular structure matters or not, and whether the main thing is just changing from a very cloudy state to a less cloudy state. But yeah.
I mean, it's that d del squared, the pockets of cellular convection, so it's d del squared, you're with some other dynamical operator in there.
That's exactly what I've been looking into. Yeah, putting something nonlinear in there for and that was exactly the part where we started before we even did this linear model. Is we were imagining that cloud edge is where interesting things happen, and where you're going to have to introduce some sort of nonlinearity if you're going to try to model things with only one variable, like Q.
Where does that del squared operator show up in the final PDF?
Like in the phase diagram.
Yeah, where does it push?
Shifts the whole curve.
Yeah, it would stretch or shrink it.
It's not
I
immediate,
think,
obviously.
yeah. Yeah.
Just one last small point. It seems to me that the kinds of, take the open cell problem,
Yeah.
or whatever, anything related to it. Seems to me on time scales of less than a day down to minutes or hours, that we know pretty much where some of the granularity appears. And that's because you have something that's destabilizing the environment, either surface heating or post-frontal differential temperature advection, which like the open cells were in those satellite pictures.
Right.
So are you going to build those into your model as the forcing?
That would have to fit in as something contributing to an F, I think. But
Because, the first cells that were explained by theory were by, the stuff that Ruby Krishnan and Murdy did back 60 years ago and things like that. We're giving cellular solutions in convection, dry convection.
oh, okay, sure, yeah, sort of dry radial convection does give cellular structures. I guess that requires interactive fluid dynamics also, though. So I guess in trying to create a model that doesn't have interactive momentum equations and everything, then thinking about how that enters in is a little bit of a different question.
No other questions? Let's thank Sam one more time.